I will just try to tell you a flavor, okay, with the hope that you will have questions. And so I won't go through everything because I want to, all what I have, because I really would like to get you a kind of a generic flavor of all the things that one can think of in accelerators. And okay, so I just told you about how basically for LHC, the point is that we need to have this 1 over lambda square that are the contact interactions to be not very big, so the cross sections are not very small. If that's the case, then and we want to have an effective a description of the reduced theory where the couplings are still in the perturbatory regime, then the value of the mediator MB cannot be very big, correct? So that's what I was trying to tell you. Sorry, what I was trying to tell you here. Okay, so then we say if this has to be not very big, then and this is of order 1 or so, then this guy cannot be very big either, and then we know that this means that it breaks the effective field theory approach. Okay, so that happens for energies of LHC, and even more now at 13 TeV than at 8 TeV, which means that most of the events that we are looking are such that effective field theory is not valid. And that's the problem that we saw when we say, when we look at this, okay? So this variation between basically leading order and loop effects is like a 60% variation decrease cross-section. That means that the effective field theory is not a good way to describe theory. So a step further in complexity is try to get the simplified models, correct? Simplified models can be very diverse, and so I have here many more than what I will talk about because of time constraints. So they should be simple enough to create a credible unit within a more complicated model. So like what it means is that I would like to have, for example, a simplified model where I have a mediator which is, let's say, a color scalar, okay? And then my idea is that this would be a simplified model for a model of supersymmetry where I am resolving the squarks and the dark matter, but I'm integrating many other particles out. Okay, so that's the idea of a simplified model, correct? So what we are going to do is consider a description of one or more additional particles that are mediated interactions between the dark matter candidates and the standard model candidate. Of course, again, the dark matter candidate should be absolutely stable or live long enough to escape LHC detectors. And the idea is that this dark sector, so these are models of dark sectors, can be richer, okay? But all the additional states, as I was saying, are like, say, gluinos or whatever, are decoupled. So let's say I'm only thinking about squarks and dark matter, for example, if you think about supersymmetry. The main point, as I was saying, this, unlike these dark matter effective field theories, these simplified models are able to describe correctly the full kinematics of the dark matter production at LHC. So it's really because you are really having these extra particles and you are having the kinematics that is directed to these extra particles. For example, having single particle S channel or T channel exchanges. So this is what we are going to look for the next few minutes. Of course, possibilities are always very broad, and so we are going to consider renormalizable interactions that are consistent with Lorentz invariance and the standard model gauge symmetries and dark matter stability. So these are the type of mediators I will discuss in the simplified models. And of course, this interaction should not violate the exact and approximate global symmetries of the standard model. Okay, so these are kind of basic things. By construction, okay, the idea is that the physics that we are going to describe is going to be described by a smaller amount of parameters, correct? The effective field theory, we just have basically 2 parameters for a given operator, okay? Here we'll have a bit more of parameters because we will have at least, correct, the mediator, the coupling of the mediator with the standard model particles, the couple of the mediator with the dark matter. As I said, the mediator means the mass of the mediator and the mass of the dark matter. So the minimum you can get are these 4 parameters. Okay, how the mediator couples to dark matter, the mass of the mediator, the mass of the dark matter. This is the minimal set that you can get. And so the interesting thing is that so we are going to test the strength of these interactions at LHC now between the protons and the dark matter, correct? And we are going to translate these, okay, in, for example, a 2-parameter space, the mass of the mediator and the mass of the dark matter, by assuming, for example, fixed values, in this case, of the couplings. Okay, so we can always do that, correct? We can always do this thing. And so the interesting thing is that for this is a cartoon of a mediator versus a dark matter particle. What we see here, correct, is that when we are in this region of parameter space, so that the mediator is produced off shell, so if the mediator mass is lower than 2 times of the dark matter particle, then the mediators are off shell, and when a production is off shell, is less strong. So that's not the region where LHC will do well. Then in this region here, okay, is where we are going to look at signals. And the signals I'm going to tell you about, because I told you before, you know, we are looking for missing transfer momentum. But if we have in the environment of LHC just missing transfer momentum, it's very hard to disentangle. So we need really to kind of see if we are only producing the two dark matter particles, we have to have some in the other particle that we are giving a boost to these dark matter particles so that we can look at these missing energy or missing momentum transfers. Okay, and this is the searches that are called, as we are going to say, that are called mono X searches. So basically I have the dark matter particles recoiling against of some other thing that I can measure. That could be, as we will see, a photon, a shed, a Higgs, a W. We are going to see about that. Okay. So the LHC searches will aim to explore this region of parameter space where the mediator is produced on shell. And of course, if the mass of the mediator, this is the mass of the mediator, correct? If the mass of the mediator becomes heavy enough, then we were saying the effective field theory would become valid. Caveat with the things that we discovered that in reality is not a good description. Okay, so the other thing I will try to show, so there are 2 things. We are going to look at searches at LHC of direct dark matter particles. And we are also going to connect that with the complementarity with LHC searches with non-LHC searches. For example, direct detection. Okay? So these results that I already show you that were in this is really very poor definition, unfortunately. So they were in terms of the mass of the mediator versus the mass of the dark matter particle. We can convert this space. So if you look at the direct detection experiment, for example, the dark matter particle interaction with the nucleon. So this cross section, when you are thinking about direct detection, correct? That you already so that you have the dark matter coming from the space and interacts with whatever is my mass of my detector, correct? And so then this coupling would be the other way around, would be just proportional again of the coupling of the mediator to the standard model particles, to the dark matter particles, 1 over the mass of the mediator to the 4th, and is proportional to this dark matter nucleon reduced mass. That is really what is that I'm sure you saw it in your lectures about direct detection. And this reduced mass is mass of the dark matter, mass of the nucleon, the proton or or the neutron that you are heating over this sum. So obviously, if the mass of the dark matter particle is much heavier than the mass of 1 GeV, as we are looking in this area of parameter space, then this is just basically you throw this away, and this dark matter is proportional to the mass of the nucleon, which means that this cross-section can be directly replacing the dependence of this mediator mass. So we are going to show results in terms of M mediator and M dark matter, or we are going to convert these limits in matter, the mass of the dark matter, and the cross-section of a spin-independent cross-sections at direct detection experiments. And so we are going to be able to compare the LHC results with direct detection results. I don't know if you already saw that in the direct detection lectures, if anyone mentioned how the LHC can do vis-a-vis the direct detection bounds. Did they? No. Okay. But this is very important, no? To compare the power of collider searches. As we were saying, the complementarity is very important, the complementarity between what we can do at colliders with relativistic dark matter being created, and what we can do at direct detection experiments, where we have our deep underground experiments waiting for dark matter to hit our detector and give a recoil nucleus and get some interaction. Okay? Okay. So in reality, in this cartoon again of this cross-section at direct detection experiments versus the mass of the dark matter, we will see that the non-LHC direct detection experiments, is gone. Oh no. Exclude regions up to a given mass, because when the mass becomes very small, then the energy deposition is too small and there is not enough recoil energy, okay, so you don't have sensitivity. And then in the LHC, we'll see that we will exclude instead much smaller masses of the dark matter in this parameter space, and there will be some region of overlap. So LHC exclusions and direct dark matter exclusion would be interestingly overlapping. Of course, as I already said, direct detection limits, as the ones that we are here, can be evaded if we assume that the dark matter is not stable on cosmological time scales, but lives enough to escape the LHC detectors. So let's look at model building, and I will talk mainly about 3 different situations. 2 are going to be S-channel exchanges, and 1 is going to be a T-channel exchange. Okay, so the S-channel exchange, which I hope I don't know. I suppose this is clear enough. Okay, but S-channel is anything that is like that. Okay, where this is a fermion and a fermion and a chi and a chi, and then we are going to have something that would be, I don't know, something like this. Okay, where you can have. This is a T-channel exchange where you can have some fermion doing something and then some scalar dark matter or whatever. Okay, something like that. So this is T-channel. This is S-channel. And here we are going to have vectors or scalars. Okay. Okay. So I realize I didn't put a drawing here. So let's first consider this S-channel in the case that there's a spin 0 mediator. So there is a scalar there, okay? So we have a scalar gauge singlet with interactions with some singlet dark matter particles. And these dark matter particles could be Dirac or Majorana. Dirac or Majorana behave different vis-a-vis the interactions. This scalar, as I said there, could be a real scalar or could be a complex scalar. Then the interactions are going to be different, gamma 5 or not, okay? And these all are very important because of the way that when you compute these cross-sections, if you have gamma 5s, basically, whenever you have a result and you add a gamma 5, you change something that is velocity dependent to something that is not. And so it's important for this SP wave suppression that we were discussing. So this is 2 interactions. So we have one is a scalar with a fermion, and this is a pseudo-scalar with a fermion. So this is so we have the interactions of the scalar with a coupling with the dark matter. And then we have these interactions of this scalar with the standard model fermions. This is a simple model where we are really not assuming, well, so these are the Yukawas of the standard model, okay? So, and these are some extra couplings that are, however, not having any flavor violation. So in these minimal flavor violation scenarios, the only flavor structure is given by the Yukawas of the standard model. This is just for simplicity, because then we know that we are not creating additional issues with flavor violation. So in these very simplified models, we are directly connecting this scalar to the fermions, but we are not saying what is the process. Okay, we are doing a tree level. We are imposing it at tree level. As I will tell you in a second, one possibility of, I'm doing this at tree level, correct? I'm saying, I'm postulating that I have this interaction at tree level. Okay, but I could also define that this interaction is given from example from a Higgs portal, and I will show that in a moment. Okay, there is a Higgs portal in the case of the scalar, correct, where I have now a Higgs that couples to the scalar. Okay, the scalar couples to the dark matter. Okay, and now this is a standard model interaction, but this is a Higgs portal and this is basically going to define what are precisely these couplings here. But for the moment, I am putting this in a bubble, so to say. And this is my bubble, let's say, an example. Okay? So this is an example, and you can have, as I said, an scalar, or you can have a pseudoscalar if you populate with gamma 5s, okay? And as I said, in general would be a scalar potential coupling this scalar to the Higgs, and one can go into that, and I will go into that in a second. And for simplicity, in what we are going to say, we are going to assume that this GU, GD, and GI are all the same. And if that's the case, then we have our 4 model parameter that we were saying, simplified. Okay, you can always put more layers to your model. And of course, there is also the dark matter production will depend on the total width. Okay, that is going of the dark matter, that is also going of the mediator, that is also going to be given in terms of these parameters. So this is one case, okay, and the point is that in this case we are going to have different interactions that will produce, for example, signals at LHC that we will be able to present in terms of these couplings, or fixing these 2 couplings in terms of these masses. Okay? Is that all good? Please stop me if I am if I'm going too fast, or tell me, hurry up if I'm going too slow. So let me pause for a second. So I told you a scalar mediator, okay, S-channel scalar mediator. A very related cousin, of course, is, or the simplest cousin, is that this thing here is just the Higgs. Okay, so I can put here directly, this could be the Higgs, okay, well, of course, this is a W or dependent. If this guy was the Higgs, and this is a dark matter particle, which is a scalar dark matter particle, this is the absolutely most simple, okay, a scalar mediator that you can have, okay. Of course, that will generate invisible Higgs decays. And we have bounds on invisible Higgs decays, okay? So when we think about Higgs portals, there are 2 types of things we can think. There are different types of things you can think, but basically is adding to the structure of my simplified models that the Higgs plays an important role. The Higgs, that is a standard model particle at the end, plays an important role in connecting, in either being the mediator itself, like in this case, okay, or in connecting the mediator to the standard model. Is that okay? So this is one case. So case number 1. So this is basically the Higgs, and this is my dark matter particle. Okay. So the self-coupling, okay, this is the self-coupling of the dark matter, but this really plays no role in how well we can the Higgs, the portal coupling can be proved via LHC searches. So this is the coupling that we are proving. So there's a discrete symmetry here, so that chi goes to minus chi and the Higgs goes to Higgs. So then this is a stable particle. And in addition, there is no singlet Higgs mixing, okay? So, which means that the Higgs itself has all its couplings otherwise. There is no mixing between the Higgs and the dark matter, so all the Higgs couplings are the same, but the only point is that the Higgs can decay to dark matter, okay? And so you will basically have some production of the Higgs by whatever mix mechanism you have, and then glue goes to Higgs, Higgs decays to dark matter as part of the invisible decay, and you can trigger that against some X mono object. So this is useful so this is the width of the Higgs into these dark matter particles, and one can do measurements to see how much of a dark matter, how much invisible Higgs width is allowed at LHC. Okay. A more complicated or a bit more sophisticated is the case I was telling you here, where now the Higgs mixes with a scalar that is my mediator. Okay. So this is my scalar now, and the Higgs mixes. Okay. So this is the interaction of the singlet with the dark matter, as we saw before in our other example. But now instead of having couplings of these, postulating the existence of the couplings of this singlet to the fermions, I have these couplings through the mixing of the Higgs with the scalar. Okay? So now we have the Yukawa coupling in the dark sector that is here, and then we have the mu p and lambda p are the Higgs portals between the dark matter and the standard model. Okay, and these ones play no important role in the dark matter phenomenology, and so we can effectively set them to zero. The only thing is for purpose of the total Higgs potential. So this is a Higgs portal through a scalar. Okay, of course this is one example where the scalar is a singlet. The scalar could be a doublet. I could have a scalar doublet, an additional scalar doublet that is nothing more than the supersymmetry. Okay, where you have two Higgs doublets, and then instead of having a singlet that mixes with the Higgs, you have a doublet that mixes with the Higgs. Okay? Yes?
Then it would just be a copy of this, a copy of those 5 times, correct? Or am I wrong?
In the MSSM?
Yes.
No, in the MSSM it's a bit more complicated because it's not a singlet, so you cannot really write the same things. And in the MSSM, there are two things that are quite different, because in the MSSM, the two Higgs doublets couple directly to the fermions. Okay? Instead here, this guy, I can assume that the couplings that I had before here, correct, are just coming, these couplings of the singlet, of the singlet to the fermions, are going to couple just through the mixing between these two guys. Okay? Instead, in the MSSM, you have one of the doublets couples to the up quark, and the other Higgs doublet couples to the down at the leptons. So it's different. Yes? Okay. Okay. So this is the simplest case where we have a dark matter particle which is a fermion singlet, okay, and which couples to a scalar boson, which itself mixes with a Higgs. Okay. The next example I will show is more related to the MSSM. So this is very simple. You know, we are trying to we are really trying to look at the simplest cases we can think of to see if we can understand data and we can reproduce the dark matter measurements that we have so far, meaning relic density and so on. Okay, so we have this. To make contact with the scalar mediator model that I just showed you before, the one with the Higgs coupling to the fermions, then of course after we have electroweak symmetry breaking, these guys mixes, okay, and so we have to go to the new basis H1, H2, that is the basis of Bass-Eiger states. That is not now the Higgs and the scalar, but it's a mixture of both, okay. And so we can do the normalization, and then if we say that now this H2 is mostly my original singlet, okay, and then H1 here would be mostly my standard model Higgs, but there would be a small mixing. And the small mixing will be given by this theta angle. Okay? So as I said, the mass of H1 is approximately the mass of the standard model Higgs. The mass of H2 is given by this, and is mainly the mass of this phi. Okay? And if we can make in this model, we directly relate these couplings that I put in in the more simple model before are going to be given by minus sine theta, and then this coupling, the coupling G chi of the phi 2 of the phi to the dark matter is going to be by y chi times cosine theta. So this is the little mixing. Okay? We are just taking into account this little mixing. This cosine theta or sine theta there. Okay? Of course, now you think, we have measured the Higgs very well at LHC. We are measuring the precision measurements of all the Higgs couplings, correct, to the Higgs to the W, and the gluon fusion to the Higgs, and so on. Now all these couplings, because the Higgs has a little bit mixture of singlet, okay, these couplings have all tuned, so we have bounds on these. So all the couplings have a factor cosine theta. All the couplings, like the standard model, the H1 to WW, the one that we measure at LHC would be this H1, and so there would be a small mixture, and this puts a bound on how small sine theta should be. So the mixing of whenever you think about mixing the Higgs that we all know and love with anything else, okay, you need to go and do precision measurements of the Higgs. That is what we are doing so much at LHC now, because this will put a lot of constraints on how much flexibility you have. Okay, because the Higgs measures to ZZ and WW and gamma gamma are quite well measured even now, and it will be even more well measured. Okay, so model building is not so easy as it goes, because we have a lot of data from LHC. Okay? So this is another example. The last one, this I think, so here I just wanted to say that, of course, because you have mixings between H1 and H2, and these Higgs, so the Higgs in the standard model, correct, can go to WW and CC, correct, that we know, but now we can have a case where we have a mixture of H1 and H2, and so we can have something that is W an S channel of a Z boson going to a Z boson, and a Higgs that could be Higgs 1 or Higgs 2. Okay, so this is a good thing that I will come back to that. Remember this model, because this could be interesting mono gauge boson signals that have been actually very much studied. Okay. The other point I wanted to show you is the one that is really related to supersymmetry, and is when the dark matter is a fermion, but it's a mixture of a singlet and an electroweak doublet. Okay, in supersymmetry you have the neutralinos, and the neutralinos can be mixtures of Bino and Higgsino. The Higgsino is an electroweak doublet. The Bino from the U1 is a singlet. Okay, so these are called singlet doublet dark matter, but this singlet doublet dark matter is, in fact, the most basic thing we have ever looked at in the WIMPs. That is just the SUSY. The SUSY neutralino is that. It's a singlet doublet dark matter. And in fact, this is something very dear to my heart, but because it's really what I have been working the most in dark matter, both in MSSM or the NMSSM. In the NMSSM, you also have an additional singlet, and as a super partner, you have a singlino. So one thing I want to transmit, at least, because I think is very interesting. People ask, oh, in supersymmetry, we have all these bounds from direct detection experiments that are putting very strong constraints on the composition of the dark matter particles. The point is that, as I said before, one thing I think is important, we were saying, correct, that in direct detection, okay, I have this, so this is some signal, correct, and when this Z is my is my way of looking for the detection experiments, we know that these cross-sections that are mediated by a Z boson are very large, correct? So now we are moving into an area where we are trying to look for a Higgs mediating. But of course in supersymmetry you have the Higgs, the heavy Higgs, the little Higgs, and depending what you are doing you will have also the CPO Higgs, and if you have the NMSSM you have a mixture that is a lot of singlets, so you have many particles here, okay? And so the idea, because I won't be able to explain that, but when you look at these, these cross sections, correct, like that, and this is just sigma spin independent, correct? And you look at these cross sections, and people say, okay, these areas of cross sections is when you have the Z boson, okay, here, and now we are here where we are testing these things. Okay, and the interesting point is that there is something that are called blind spots, okay, where these cross sections are such because of the structures of the model, and it really is very interesting that there are some natural because the difference between supersymmetry and any of these simplified models, correct, is that you have really strong correlations between the couplings and the masses of all these particles, okay, and it's very easy to be in regions of parameter space where both in the MSSM and in NMSSM there are cancellations, they are called blind spots, where naturally your cross sections are really down here, actually, even down this neutrino floor. Okay, so this is, I think, very interesting. As I said, my paper on dark matter for a couple of months ago is exactly about that. Okay, it's exactly about how you can have interesting dark matter relic density by having mixtures of synglinos and synglino-hixino or bino-hixino in supersymmetry in the MSSM, and at the same time you are okay, so this is for omega dark matter, correct, for the relic density, and at the same time in direct detection experiments the spin independent cross sections are really can be really much below what has been explored so far by experiments because of having some cancellations on how you go into spin-independent cross-sections. Okay, so that is called blind spots. Okay, yes, sorry. Anyway, so these type of portals, where are singlet doublet models, these are exactly the type of portals that you get in supersymmetry. Okay, the neutralinos are this type of portals, and I won't go into these details because I want to move differently, but of course we study this type of portals. In supersymmetry there are very strong correlations in the parameter space, and you could, even in that case, you can get a lot of good things there. Of course, in these models, again, in all these Higgs portals, you have the Higgs going into dark matter, so you will have a strong constraints from invisible Higgs decays, and you are also in all these models. You are also going to search for direct production of the neutralinos and the charginos at the LHC. Okay, so this is when I look at one mediator that is a scalar or pseudo-scalar, and as I said, through the Higgs portal you can give more substance at what you have in this vertex, and also you can connect with models of like this singlet fermion singlet doublet dark matter as it happens in the MSSM. So what I try to say is that in all these singlet scenarios you can really connect very easy to some other cases where we have looked very carefully like supersymmetry. So the other option, of course, is to have an S channel that is by a spin 1 particle, so this B mu here, correct? So the simplest way to add a new mediator is to extend the gauge symmetry by a new U1. So suppose you put a new U1, a dark photon, a photon prime, okay? And so we can spontaneously break that symmetry such that the mediator will acquire a mass, correct? So we can add some scalar so that the mediator will acquire a mass. So then we have, this is a model that we already kind of look at, correct? Before, in the case when we are doing the connection with effective field theory, we just look at the case where this mediator is only axial, okay? So we look at this case here. When I show you the relation between effective field theory and we were looking at this vector mediator, axial vector mediator, we were looking at this times this. So here we are looking at the whole possibilities where these are all the quarks, charged leptons, and neutrinos, okay, that can go there. So this is for a case where we have a scalar, a vector with a fermionic dark matter, but also the dark matter could be a complex scalar, as it is here. Okay. Obviously, if it is for this vector type of mediator, you see right away that if the scalar would be real, this would be 0. Correct. So you cannot have that. The other thing that is interesting, that is not so easy to see, but you can do the calculation, is that if you have Majorana dark matter, okay, the vector coupling vanishes because it's a conserved current. Okay, so you can only have axial vector couplings for Majorana dark matter. Okay, and this is also an interesting thing, which plays a relevant role in limits from direct detection. So in these simplified models, now we have the mass of the dark matter, the mass of the mediator, the coupling of the mediator to the dark matter, and eventually the coupling of the mediator to the up quark sector, the down quark sector, and the lepton sector. Correct? And this is these simplified models really look at either vector-like mediators, so this type, correct, or they look to axial. In reality, is a pure axial mediator is hard to build in the model. So in reality, you have a mixture, okay, of both. Okay, like if you have a set prime, okay, could be a mixture. It's not. Okay, so I think I will skip on this. The last part is the T mediator, okay, the T-channel flavor mediator. So in this case, the interaction is like the scalar, the dark matter, and the quark, okay. Of course, in this case, either the dark matter, since the quark we are thinking about producing this at LHC, so we are coming with quarks, correct? So since the dark matter, if we don't want the dark matter to be colored, that there are some more Baroque models that do that, then you want the mediator to be colored. And this is just the squark dark matter quark interaction of the MSSM. Okay? So we can look, for example, at a case where the mediator couples only to the up-type quarks or the down quarks, or you can do whatever you want. But let's say that we consider in this case a case where the mediator is just like the up charm and stop of supersymmetry. So one can have the mass, again, this parameter space, one can have masses of the mediator, and if we think supersymmetry, the stops and the first and second generation squarks have very different masses because of the way you break supersymmetry. So it is normal to think that maybe you can have this hierarchy that the first and second generation and the third generation have different masses and different couplings, or you can decide that they're all about the same if you have some unification model. So in general, these models with a T-channel flavor mediator are very similar to those of the squarks, and one can consider this analysis and rephrase analysis at LHC, where we search for dark matter that is produced in gluon fusion or in QQ bar fusion, and then you go through squarks, or you go to through bottoms and stops. Okay. Okay, so we look at all these possibilities, okay? How do we really search at LHC for these possibilities? These are models, correct? How do we search for these? the options is the best option to look at this dark matter. So there are two ways, as I told you, correct? Either I produce that if the energy, if I'm the right range of energy, I produce them directly, and then I make them recoil through something else, or I produce in the decay of heavy particles. So the most model-independent searches are the ones where I produce mono objects, okay? So I produce PP bar that goes to dark matter particle plus some mono object, okay? This mono object is just some system of observable particles that recoil against the dark matter particle, is what you were saying, what I was saying before, correct? Against the missing transfer energy. So we identify the missing transfer momentum or missing transfer energy, and we can search for these objects. They are called mono object, but in reality, this is a system that is either composed by jets, by photons, by weak bosons, by Higgs bosons, or even by TT-bar pairs. Okay, so it's just recoiling against something. And this is the best way to look in a more model-independent way. So let's go, we are going to look, we look at these cases here, correct, of the T channel and the S channel. So let's go and look what are the type of signatures we can look. So first let's look at the scalar or pseudoscalar mediator S channel. And then when that happens, so this is this is the model I was, I'm really sorry that I at least cannot see this very well. So this is the model I was showing you before, okay, where the scalar or the pseudoscalar couples directly to the fermions, okay, with some couplings G. So here is the parameter space. I'm assuming that all the couplings GU, GD, and GL are the same, and so I can produce these at loop level, gluon fusion. And then I produce my mediator that decays into dark matter particles, and I have this gluon, and so I look for the missing momentum against recoiling against the PT, the transfer momentum of this jet, of this gluon. Okay? This is another case where I have again, now it's an S-channel production of directly here of the pseudoscalar or the scalar, and then I have this additional shed here. So these are monoshed searches in this parameter space. So this is the most sensitive because they are QCD type of interactions, correct? So they are QCD production at this level. So these are the most sensible of all searches for dark matter in this in this scalar or pseudoscalar mediator S channel. Okay. Of course, there are also, as I said, the sensitivity, I can always go and produce, instead of a gluon here, I can produce a photon, correct? Or I can radiate a photon, or I can radiate a W, or I can radiate a C. Well, depending if it is a W, I have to change these, correct? But I can radiate a C here, or I can radiate a photon. I can do that, but then this will be much less sensitivity because I am going into a electroweak state. What I told you before, this model where we have this mixing between the standard model Higgs and the scalar mediator, in this case, of course, I can have this mono W, mono V is W or C, this type of decays, and this is the best way. So if I have this type of interaction, this is the best way to look for a mono W or mono Z and dark matter. And in these models here also, what can happen is because in this interaction I have the Yukawa interaction of the standard model, so these guys are going to be mainly strongly coupled to the top, okay, so we can see it here, correct? So I can produce gluon fusion going to TT-bar, and this I can radiate from this top, I can get this scalar. So these are searches of missing energy against a pair of recoiling tops or recoiling bottoms. Okay? So this is top or bottom pair search. And this is, again, in this type of interactions, of course, I can radiate Higgs from here, okay? And in these models where the Higgs couples to the top strongly, that is also a possibility. So in this type of models where I have the Higgs mixing with the scalar, these are the two cases that I can look for mono Higgs or mono B. Okay, but when I do these searches, I don't know about this, correct? I just go blindly. I look for mono photon, mono jet, mono W, mono Higgs, and then I interpret it in terms of these models. Okay.
I wonder why, because there are absolutely many, once you open up these blobs that are the effective field here, you have a plethora of simplified models, which end up being as complicated as a whole supersymmetric search. The only thing is that you open up, instead of having all these correlations between the parameters, you open them up. But the degree of parameters, the degree of different possible models, and so forth.
It's not less, it's not, I mean, the idea of the idea of simplify is that you went from 2-parameter space to 4-parameter space, correct? But then you can go to 6, or you can, so as in reality what you are doing is you are building up these simplified models that at the end up being, in my personal taste, but I'm telling you what the community is thinking about. I have not worked in any of these simplified models myself. What you are doing is you are trying, to unfold a little bit more and a little bit more, and the only freedom you are getting with respect to going to supersymmetry, that at the end, as I said, one of these models is really looking for squarks, okay, and neutralinos, but you don't have any connection that you have within the UV completed supersymmetric theory. So if you want, you are doing the bottom-up approach and trying to, put one layer of the onion out and the other layer of the onion out and the other layer of the onion out. And at the end, if you want to go to the UV completion, you will end up in the MSSM, in the NMSSM. But people are saying, it's stupid to be looking at the NMSSM, because the idea is not so simple. Is that by doing this, you may open up possibilities in the case and so on, that if you are thinking only in NMSSM or MSSM or so, maybe some of these searches are not open, so you will not think about it. So the idea is really, the only exercise that we are doing is trying to think the broader we can, not to miss any searches. That's really the idea, and to have some scenario to present them. Okay. So this is the one with the axial vector. Again, the monoshed ends up being the most important. This is the vector axial vector mediator. This is the mono Higgs signal that I was saying, that if you have, for example, this is a very cute from one of my colleagues at Chicago and Company, where you have an extra U1 and a 2 Higgs doublet model. Okay, so there is a set prime 2 Higgs doublet model, and then you can have nice mono Higgs analysis. Okay, the interesting thing is that this, and then the last one, I think, I'm going over all these because otherwise, the last one is these color scalar mediators. These are really squarks. Okay, we're looking for squarks in many different ways, but not putting bounds or anything. So these are my squarks. Okay, so I have QQ bar initiated, or I can have gluon initiated. For example, this gluon initiated, you go to at the end, this is a squark going to quark neutralino, so these are 2 sheds. These are 1 shed, and these are 2 sheds, but these mono sheds, okay? So you look for anything, sheds plus missing energy, and these are models where you really are very similar to the squark. Okay, and of course you can radiate here a W, a Z, or a photon, and this will give you the same mono photon and mono Z and mono W signatures. Okay, if we have a signature, then we will go back and try to find out. So I am trying to. This is a disaster. I have how much time?
Like 10, 15 minutes.
Let's call it 15.
But you could have 20 minutes.
Because I want to tell you a bit more besides LHC, so that's the point. Okay, so forget about that. You can read all the details. I spend a lot of time writing all the details. So I just want to explain, this is a monoshed signal, okay? So you have a shed here and the missing energy on this way. So monoshed event displays, okay? The shed down bars are balanced by the missing ET. We already looked at this before, but this could be something that you cannot really explain. This could be also a W going into...
But this is not an actual event, or is it?
Yeah, it's an actual event.
But then is this the neutrino or what?
These are both at 1 TeV, so this is just some fluctuation of something, yeah. This is, if you have many of these, you have discovered dark matter.
All this complication, of course, you have all the backgrounds that are due to completely irrelevant for this kind of search physics, that are backgrounds and will mimic all this, and you have to do...
Yeah, you have to do a lot of...
to see how many of these events you have without any...
So they look for monosheds, and I won't say anything, and they put bounds, okay? So this is the results, so for example. So these are monoshed searches at LHC, and there are many. They put it in the dark matter versus the mediator mass. As I told you, this is the part that LHC can look at. This is the 95% exclusion limit in some vector mediator model with some assumptions of the coupling in an axial vector mediator model.
Yes,
and
which are always, and this I discussed actually with people at the LHC, huge. And
huge meaning what, Graciela?
The couplings are huge.
Oh, well.
We have two couplings.
No. But wait. This is very great that you asked this question. For the vector-like, for example, the coupling to quarks, you can't read anything here. But the assumed coupling to quarks, because I told you that you have two parameter space, you have to assume the other two. Here, they are assuming that the couplings of the W, of the B mu here, or axial B mu, is of order at most 0.25, because if not, you look at these W's, W primes or Z primes going into a resonant production of sheds. So you cannot have, for example, if you would have this coupling 1, you will be totally excluded by direct resonance searches of die sheds.
If you go to 0.1, you don't have a signal.
Yes.
That's the point.
Yeah. So you are in the middle of what you can do without being excluded.
Because if you go exactly.
Yeah. So this is
where you are optimum. But if you deviate, and this is what I find slightly misleading, because it's true that you present, but there should be some other plot that should also be shown somehow to indicate how you lose. Because whenever you have, to be honest, when you are a theorist and you do this honestly, if you have a sensitivity to a particular parameter, you try to show your sensitivity. Because if you have a signal, or you can put a bound only when you are between 0.1 and 0.25 or something like that, then you show it because it is honest. And you don't go and show exactly where your limits are the best. Right? But in this case, somehow, this is not shown.
The way I see it,
and if you
but
0.1 and 0.1, if you decrease by a little bit, you don't have a signal. This is the point.
The way I
reduce them or so on. So this sensitivity,
the way I would say it, looking from the experimental point of view, that if we could have an excess, then we will be more worrying about how we put, which limits are we putting for which assumptions, correct? But these are limits representative, because we are not seeing any monoshed missing momentum effect. We are not seeing any big deviation. And so we place the limits however we like it. In the parameter space, we like it.
I'm coming from, I'm sorry, I'm a little bit of an advocatus diaboli, because after all this is, the problem is then, for the community that is trying to do direct searches, is the second one,
this one here.
In which you compare with LUX. And if you would put these couplings actually 0.1 and whatever 0.1, the LUX limits are still going to be there. But you would have no limits from the LHC. You see, it's very sensitive to the couplings that you assume. One is the coupling of the dark matter, the quarks or whatever.
Yeah, here.
With dark matter. The other is the mediator. The one is the mediator with dark matter.
Yeah, this is
with quarks.
This is this, correct? I mean,
and if any of the 2 is really small. It's more the more sensitive to the mediator with the quarks. You do not produce enough of them.
So this is
So these comparisons, sometimes, if people say, and I used to have a collaborator who said, why are you trying to look for light neutralinos? LHC has killed all this region because they were killed in this plots. They were actually rejected by monojet, for example, But this is misleading because in reality you would still have a very valid search, even a potential signal indirect detection, even when you would have no limits coming from the LHC because the coupling is small.
Well, Graciela, sorry, in this direct detection you still are having this assumption, so the assumptions are the same, correct?
Because you don't know the mediator, it's just a cross-section. You put a limit on the cross-section.
On the cross-section, correct.
But you don't have sensitivity to the value of each one of the coupling.
But
sensitivity that the LHC has, because you are producing. This is a combination of production and decay and width and so on. And the LHC is extremely sensitive to the value of some of these couplings. And direct detection is not.
So you can put 0.1 here.
You can put 0.1.
Yeah. Yeah, in this interpretation, when you do cross-section versus this, correct, you are obviously assuming the same value of these guys, and with this guy, assume whatever you want. You convert this bound on non-LHC exclusion as in a bound on this.
This is not wrong.
So this is what you're doing, correct?
It's really not wrong. I mean, it's correct because they put what they assume. What is not is clear that actually how fast you lose your LHC bound if you change how sensitive you are to the values of the coupling constant. So this is the
Oops.
This is the point.
Okay.
Not that it's yes, it's not wrong, but it might be misleading if you want.
Okay, so anyway, since I want to talk about something else, I'm trying to see what I'm doing here, sorry. I will probably, this is doing monophotons. Again, they can do different bounds. They are the same type of searches, correct? So in any case, what we see, the only thing that we see, no matter how you play it, that the LHC has sensitivity to this low mass dark matter, correct? Because it's there where if the dark matter is very, very low, then you don't get enough energy into your direct detection experiment, so your threshold is not good enough to put a limit, and that's the reason why these guys go hit like hell here, correct? Because you need to lower your energy threshold for direct detection. And the LHC is independent of that, because once your mass is below your energy cut, you don't care. Okay, so that's, so they are mono Higgses. I can, I think this is interesting. So this is a plot where we look at as an example, at the spin 1 mediator. And these are the type of bounds that we put in the mono X searches. So mono SHED, mono photo, mono C, for example. You see that this is also for a limiting case, correct? Because now you have this 0.25 here. There are no leptons. We put this coupling to leptons to 0, because otherwise LHC is very powerful in putting bounds on dilepton resonances. Okay, so if I turn this on, okay, then of course LHC will kill many of these possibilities. But this is searches now. Combined searches of the dark matter. So this is the dark matter search with my axial vector, mediator, spin 1 mediator, actually vector mediator, and these bounds here. This is one thing I wanted to say. So these bounds here are coming from searching for dishets. So I'm not producing the dark matter. I don't care what happened to the dark matter. I care that this mediator. If the mediator is produced through interactions with quarks, it's also the case in 2 quarks, correct? And this production, as Graciela says, the fact that I'm looking for the mediator going to dark matter, I first have to produce the mediator. If I put this small coupling very small, I don't produce the mediator and I don't have any bounds, correct? If I put this coupling too big, the mediator then goes a lot into sheds and I have bounds on the sheds at LHC, okay? And so this is the bound now. And one thing I wanted to say is that up to not very long ago, these bounds started above 500 GeV or so. Was very hard, so actually even more. Started like about 1 TeV or so. Because the problem is that there are so many sheds that we get at LHC that it's very hard to keep them on tape. And so events with 2 or more sheds, we cannot save all in the disk, so we have to think about more intelligent ways to look at low die shed mass distributions, okay? So now with new techniques that has to do with boosted sheds, with ways of only getting subpartial information, and I don't know much about it, but I have read about it, and they are very, very cute. This is why they can do now initial state radiation, for example, this green, this is all new. And this trigger, so this is first trigger level acquisition. These are the things here, correct? These things here and here. These 2 are novel things to go and look at areas where the mediator, the Z prime, is below a TeV. Because if not, LHC was swamped by background, was not able to do anything. Okay, so that's an interesting point, I think, that has pushed the technology in LHC searches. Well, of course, as I said, the squark and the gluinos are here, okay? So you can look at these color particles, as I said. So these are an example of when you look at squarks going into quark and neutralino, or you can have these decays where you produce other things that then decay, so cascade decays, okay? And you can look at squark decays and see where you are in the squark LSP region, or in the gluino LSP region. And of course, these are model dependent, correct? Depend on which are the cascades you produce, so you'll do that with some assumptions, okay? So they are even more model dependent than the things that I told you before, okay? So again, I think the point is, if we could see a signal, then this will become, if we put G equal 0.25 or G equal 0.2, and what we that would be important, correct? And at this moment, we are just trying to show we don't see any signal. These are the type of exclusions. These are the type of things that we can know. You can also look for stops. You know, we suggest that stops should be light. In reality, in the NMSSM, you can significantly so the fact that the Higgs is what it is implies that the stops need to be sufficiently heavy to give sufficiently, you know, in the supersymmetry, in the minimal supersymmetric model or in supersymmetry, the Higgs mass would be like the value of the Z mass because it comes from the relation of the gauge couplings, okay? So you need radiative corrections from the top quark and the stops, and that are the ones that couple the stronger to Higgs, in order to elevate the Higgs mass to be 125 GeV. Okay, and the fact that the Higgs mass is 125 GeV means that at least one of the stops has to be sufficiently heavy to give sufficiently big radiative corrections to generate that mass. Okay, but of course on the other side we want to have some naturalness of the parameters of the model that are related to how heavy the stops are. So there is a tension there, the naturalness problem. Okay, I'm not going to go into that now. If you want, we can discuss later. But the point is that in the MSSM, you need at least to have one stop in the TV region, but if you go to like one singlet, you just add one singlet to your model, to your supersymmetric model, then you can happily be with everything low, okay, and then all these bounds become very relevant for the stops. Yes?
Does the singlet have to be a scalar, or does
Can you repeat the question?
Does the singlet have to be a scalar, or does it?
No, the singlet is a super, the singlet has to be a scalar. The singlet is a super field. So it's a scalar singlet and a singlino, and a fermionic singlet. Okay? Because it's supersymmetry. You add a singlet, you supersymmetrize the model. So for any singlet scalar, you have a singlet fermion. Okay? So that's why you have the singlino mixing with the Higgsino. These are fermions. Okay? one singlet and one electroweak. Okay. What I'm trying to say is that the NMSSM, which is very simple, is yeah, that is, well, the minimal is, so the minimals, the MSSM is, I don't add any particles more to the standard model, I just supersymmetrize the theory. I add a symmetry, correct? The NMSSM is, I look at the standard model with a singlet, just one singlet, scalar singlet, and then I supersymmetrize my model, which means that my scalar singlet has also a scalar fermion. Okay, and this scalar fermion is a part of the dark matter candidate. Okay, and opens a lot these ideas that I told you of, having blind spots where you open up a parameter space of direct detection dark matter in a very important and interesting way, together compatible with thermal freeze out. Okay, so this is NMSSM and blind spots. I didn't have the time to write, I'm sorry. Yeah, blind spots, I was intending. So now in the next 5 minutes or so, maybe 10 or 5.5, in the next 5.5 minutes, I will give the second part of my talk. Now, so all what I talk is for WIMPs or for, as I said, the division between WIMPs and dark sector is a bit loose, because what you call dark sector, correct? I mean, dark sector is anything that is not a standard model gauge forces. But as we saw in these scenarios, it's not easy to have, if you have WIMPs, the WIMPs cannot be below 2 GeV. So what happens if you have thermal freeze out for particles that are below 2 GeV? Okay, and of course, I don't have a lot of time to go into that, but let's say that for sure we know that freeze out need to have new forces, okay, because we know that this is already too big, okay, so this is the Lee-Weinberg, so saturated bound. So obviously the signatures of the hidden sector for light matter, the same as the ones that I show you, depend on which are the type of forces that we have between the dark matter and the standard model. And so we are going to look to a simple case, yes, and the simple case we already look at it, okay. So before I told you that we have this axial or vector axial vector mediator or pseudo scalar mediator, but I didn't specify how the mediator coupling to the standard model arises. Okay, I assume, for example, that I have some heavy fermion, correct, that is going to mix. So this is again the same as I did here, correct? The same thing. I could now say, in this case, okay, I have something that is doing my mixing. Well, probably I have it there, and this mixing is the same as having this coupling directly. So this is my V mu prime, and this is my V mu of the standard model, correct? So how do I create that? So it's the same idea, okay? So what I'm going to do is, okay, I can have, this is a vector portal, this is a Higgs portal, this is what I already explained to you, okay? The Higgs portal, we already discussed it, but it's how we assume, before we assume that we have a 3-level interaction of the vector mediator with the standard model fermions. Now we are saying how this occurs, and let's say this occurs, for example, in this case, between a mixing between my photon and a U1 dark, okay? So before I assumed this as a blob, and I said, well, sorry, this as a blob, I'm sorry, and I said this guy couples somehow to the fermions. This as a blob. So this tells me a bit, if I want to say I specify these portals, it tells me a bit what these couplings that I put by hand of the vector-like vector mediator with the fermions or the scalar mediator with the fermions would be given by some charge of the fermion times this epsilon mixing here, this is epsilon, or times some mass mixing between this scalar and the Higgs, correct? That is, this here I will have something that would be mu times the vacuum expectation value. This is the Yukawa coupling over V. So obviously this whole thing here could be something at mu times mf over the Higgs mass because of this. So if I put this into a bubble, that is what I did, I get this. If I put this into a bubble, I get this. Okay, so that's just another way of looking at the thing, but it's the same. So then the point is, this is important for what it comes. I won't really have all the time to say this, but there are two things I want to transmit. They are who is heavier. Now, when the dark matter is light, you can ask a lot of questions. In fact, you can ask, what is heavier, the dark matter or the mediator? Okay. If the dark matter is heavier than the mediator, then I cannot really produce the mediator, as I was saying here, and make it decay into dark matter. Correct? That will not occur. So the most obvious way is I will produce dark matter, it's called secluded annihilation, that directly decays into the mediator. The problem with this, and I will not go into this because I don't have time, but the only thing I want to say about this is that now this cross-section, that is what I care about in order to see, thermal freeze out and so on, as you see, has no information of the coupling of the mediator with the standard model particles. Okay? Because this will decay into standard model particles now, but I don't care. The decay is not going to give me the information that I need about the standard model particles. So this production cross-section is just G dark matter to the fourth now, because this is G dark matter squared to the fourth, over the mass of the mediator, over the mass of the dark matter particle m chi squared. Okay? What this means is that I don't have any, I can look for these things, but I don't have any information that tells me that something of this type should be generated with standard model particles at accelerators. So this secluded case is not of particular interest for accelerators. Okay? There's a lot to be said about that, and I can tell you a lot. I learned a lot about that to come here, but what happens is this is not very interesting because for accelerators it's not very interesting. Okay? The other option is the other way around, that the mass of the light particle is lower, and then in that case I can do the usual trick, okay? And I can produce this thing here through my U1 dark. And then in this case, I have information about the dark matter coupling, the coupling to the standard model, that in this case we just said that is epsilon EQ, the mass of the dark matter over the mass of the mediator to the fourth, okay? I don't know why this appeared there. This excluded by meson constraints was something in my subconsciousness. Sorry, so forget that. It is here, excluded by meson, but it shouldn't be there. I apologize. So, so this is a channel annihilation into standard model particles, okay? And what is this important is because in order to get the correct relic density, okay, this is the correct relic density, okay, I will have a minimum value of this coupling, because if this has to be smaller than something so that I don't overclose the universe, and therefore I have a minimum value for my coupling, and this is something I really care about accelerators, because then that's what the point. If I want this to be thermal for some region of parameters, I will need to produce these through standard model couplings, okay? Because remember that in accelerators, so dark matter annihilation, relic density goes this way, time, accelerators goes this way, right? So that's important. I can do a lot of, I can go into this, but I don't have the time, unfortunately. So I will tell you only that if you put it here instead of a vector-like, a scalar turns out to be excluded by things like B meson decays. Okay, so it doesn't work. Okay, we can go into that. Excluded by meson constraints for if this is a scalar. That's what I only put here, a gauge boson, a U1 dark, okay? Still, the U1 dark is okay if dark matter is a scalar or is a Majorana fermion, okay? But if not, it's also going to have problems with the CMB power spectrum. I am happy to explain about that. So it's really, you really need to have a suppress, a P-wave suppression in order not to be killed by CMB, and this is the explanation, but I won't go into that. So the viable modes, you need to have, so annihilation rate must be smaller at CMB temperatures than at the time of the freeze out, because otherwise you are going to be killed by measurements of the power spectrum from CMB plant measurements at the CMB time. So you can put some bound on so this so the point is that okay, maybe I say that CMB power spectrum. The CMB power spectrum ends up excluding the most simple case, that is that you have particle-antiparticle symmetry and a Dirac fermion. Okay, because in this case this is an S wave, and because it's an S wave, you actually are not sufficiently suppressed at CMB temperatures, and you need to be sufficiently suppressed at CMB temperatures. And I know this is not clear in what I'm saying with all the details. I would be happy to tell you about that. But the end of the story is that you need P wave annihilation in order to survive constraints from CMB at CMB temperatures. Or you can have something that has been shut off before CMB, like for example would be antisymmetric dark matter, or things that have inelastic type of interactions. So make the long story short, we are going to look for the things that are P wave annihilated, or we could do for others. Yes, wrapping up. Okay, since we are wrapping up, I want to tell you, at least for you, oh, this is bad to wrap up. Okay, so let me just tell you two things. We are going to look at the dark QED. So you can look at all these models. All these are all viable models after the whole son and dance that you can look at, that survive CMB and so on. So you can have a scalar dark matter, you can have Majorana dark matter, or can have this pseudo Dirac, which means that these Chi1 and Chi2 are very close in mass. If you look at the direct detection scattering in electrons now, because this dark matter is MEV, okay? So you need to look at electrons, because otherwise your recoil energy would be like nothing, okay? So then this is MEV, and these are the bounds. So you see that direct detection experiments are very dependent on the nature of the dark matter. Okay, so what I want to say is that accelerator experiments, which there are many, I just read it and memorize in the next 2 seconds. Have you memorized all of them? I'm going to take a test. So, which are the direct dark matter searches at accelerator? There are 3 types that people are thinking about, and I will try to finish with that, Marcela. So, one is really like LHC, but with electron beams, okay? And this is, for example, Babar, E plus, E minus, okay? And you go to monophoton plus a mediator that goes into missing transfer momentum, okay? So this is monophoton plus MISITT at lepton colliders, okay? That's one type. The other one is electron and proton beam dumps, and I will show that in a second. And the last one is fixed targets. So these are 3 types to look for very light dark matter. And although I don't have a lot of time, let me just say, so this is the one, this is the one that I said for monophotons. So you do E plus, E minus here, monophoton, A prime goes to dark matter. I'm not going to go into the details, but you see these are the bounds from Babar. And this is what is expected for Bell, depending on the cross-section, okay?
We have several talks at the conference. This is a sort of preparation for that. We'll have somebody from Bell too.
Okay, so this is very interesting, because you are testing now the interactions of dark matter, of the mediator with electrons, okay? The other interesting things are beam dumps. And beam dumps can be electrons or can be protons beam dump. So I will just show proton beam dump. So this is like what you can do, for example, at Fermilab. So many different options, but Mini-Boom is at Fermilab, Nova and Dune will be. So you have a proton, okay, that basically collides with some nucleus, produce some pions. Pions decays into photons, but one of the photons converts into A prime through the mixing. And then this photon prime decays into dark matter. And the idea is that this dark matter hits a detector, the type of neutrino detector. So instead of being dark matter, that the difference is, instead of being dark matter from the sky that hits my direct detection experiment, is dark matter I produce in my proton beam that still hits the direct the tanks now of neutrinos that are much bigger than the ones of dark matter even. And so you have this that basically now A prime interacts with the electron, could directly do recoil of electrons or recoil of the nucleus. So you measure the energy. The nucleus basically gets undressed from the electrons and has a charge and then gives a contribution. The same thing as you will detect a neutrino interaction if it is neutral. Okay, neutral neutrino interaction where the neutrino emits a Z and then recoils against a target. Okay, so these are very interesting experiments. And Mini-Boom has already some bounds, okay? So basically, typically you detect it by electron, so by scattering of the dark matter with a nucleus or with an electron in a downstream detector, okay? But this is very different because we are producing the neutrinos. We are producing the dark matter, sorry. The neutrinos too. The point is that the neutrinos, you should ask me how you get rid of the neutrino background. You didn't ask.
Not now.
After I finish, you should ask me, not before. So I will forget that you also have inelastic scattering. So in the sake of time, we have also electron beam dumps. These are of the same type, but then this is directly, you have an electron which have some junk here, interact with the junk, produce this, again, photon prime, and again, you have some detector later on, and you have some interaction the same as before. But the only difference is that this is with electrons instead of with protons, with a lot of the difference that come along with, okay? So these beam dumps have the interesting point that you probe dark matter interactions twice, because first you both proton and electron, correct? You have a interaction here, and then you have an interaction here. Okay, so you are probing these dark matter, these dark sector interactions more than twice. This requires a large flux of protons or electrons in this case, and the signal is very much the same as neutrinos, so this is the main limiting factor in sensitivity. And the last one is fixed target experiments. This is a different type of experiment, which is very interesting because now you are in a different environment. Before you had these beam dumps where you have something that you go through, you create the dark matter, and the dark matter interacts with another detector, but you are not measuring, so you are not measuring anything that happens here, correct? You don't have any information, you don't have any detector there, okay? Instead, in the fixed targets, you actually have a lot of information. You have trackers, eCal, HCal, all the song and dance, okay? So you are going, you know very well your energy here, the energy you put, the energy of the beam, and you know very well the recoiling energy. And if the recoiling energy of this electron is much smaller than the beam energy that is of the order of 10 GeV or so, then you know that there is some missing energy or missing momentum, okay? Okay. So I think this is it. This is my last slide. I swear, for God, or maybe not. I was educated Catholic, but okay. Okay, so this is the last thing, so that you understand what the hell this is all about. So first I show you this cross section. This cross section here is this. okay? And I can always write, first of all, this is the annihilation cross-section, which I show you that it can be written like that, okay? Interaction of the standard model, interaction of dark matter, mass of dark matter over mass of the mediator. I can rewrite this like this, and this is y over the mass of the dark matter square, correct? So insensitive to the ratios of inputs is only unique y for a given mass, okay? Y for a given mass. So I do these lines for pseudo dark matter and Majorana and scalar, and this is the minimum value of y, and everything that is below for each case is over too much relic density, is universe overclosed. So I can only be above these lines for each model in order not to overclose the universe, okay? And these lines will not change no matter what I change these values, okay? Then I have also these direct detection experiments, these here. These are also going to be of this type, okay? Because again, I can write this as a different dependence, but I can still write this as something that is not going to change if I change the specific of this. So these are two things. And the last one, now yes, is that when I look at an experiment, for example, this one, the one at the Babar, okay, these experiments now are very sensitive to, for example, just the epsilon square, the mixing parameter of the mass, okay? So these experiments are going to give me a bound on Y experiment that in order to be conservative, I have to make this as big as I can to make the bound that I exclude to this the most conservative bound. And so now, this is yes, my last one, I swear. So I'm comparing experiments now, okay? And so now I do need to say what is this when I want to put these bounds here. Okay, this is Majorana and scalar, doesn't matter, correct? So these bounds are not dependent, are just y and m chi. If I change these values, this line will stay the same, and these lines of direct detection will stay the same. But these bounds, if I change these, if I make these bigger, then these bounds come down. Okay? Smaller, I meant. So these bounds come down, and I will say that was Graciela's point. I would be excluding things that in reality I'm excluding because of the parameter space I am. So these are conservative. Most conservative even would be to put here 1 and to put here 2. If I put here 1 and here 2, these lines would be a little bit less exclusive. But you see that for elastic dark matter, the next range of experiments of direct detection and accelerator experiment will crush it, okay? Because all this part is not allowed because I overclose the universe, okay? So these experiments are super, super powerful. These experiments are beam dump and Babar and Bell in the future. Okay, Bell is going to prove the things. So Bell, Babar, the fixed target experiments, LDMX, and all the beam dumps, neutrino experiments. Okay, these experiments, in the case of a scalar elastic dark matter, they're going to crash it. Okay, in the case of Majorana elastic, they still will prove regions of parameter space. Okay. So this is my last slide. So I think this is the future of all the experiments for light dark matter, and I think that you will hear more in the conference. Sorry, but I think this is a very interesting area where we are really finding new techniques. And of course, I didn't talk about very light dark matter like axions and so on. So this is all for thermal freeze out. All what I talked today. Okay, thank you. Sorry for going over time.